All right, let's take a few minutes and look at how, or one of the more common ways to make alkynes. I said alkenes there, it should say alkyne synthesis. And just to review, this will set up where we're going. If we had an alkyl halide and reacted it with a strong base, or did an elimination, we'd get an alkene. Well, we could use the same tactic for alkynes if we start with a dihalide. So think about it this way. If removing one H and one Br would make one pi bond, removing another H and another Br would make a second pi bond. So if we throw a lot of base and a lot of strong base at this, we would get two pi bonds. We'd get an alkyne. Now I want you to think about this. How do we make this? Well, if we go back to our last unit, we could start with an alkene and halogenate it by adding bromine across that double bond. So notice how interconnected these two chapters are going to be. We're using a reaction from the last unit, reacting it with bromine, doing an addition to make a dihalide, and then relating this all the way back to our elimination chapter. Using a strong base, we could do a double elimination to get two double bonds. Now, alternatively, we could do this exact same thing if the halogens are on the same carbon. Now, typically, we need a really strong base to accomplish this. Hydroxide really isn't going to be strong enough to cut it because we're doing two eliminations. And I'll show you in a little bit why we need something stronger. But the most common base, and this is the one I want you to memorize, that can accomplish this is sodium amide. And we typically don't care about the sodium because it's just a spectator ion. It's that NH2 minus ion that is going to be our base. So let's take a look at the mechanism for this. So remember in an E2, it's all concerted. So the base pulls off a beta hydrogen. We make that pi bond and kick off our leaving group. Now, doing the second elimination is a little difficult, which is why we typically need strong bases or stronger than, say, hydroxide, because we're doing an elimination on an alkene. And so again, we'll do same mechanism. The base will pull off a beta hydrogen, form another pi bond. Notice there though that we're making that second pi bond and kick off bromine. And now we have our alkyne. Now, while I'm talking about this, I want to highlight kind of a common mistake students make when drawing the skeleton formulas of alkynes. Remember that this is a 180-degree bond angle. So we don't represent an alkyne like this, because that's implying that there's some bond angle other than 180 degrees. So just keep that in mind when you're drawing your skeleton formulas. Now, one final thing about alkyne synthesis is that you need to be careful when making terminal alkynes. Okay, now what do I mean by terminal? It doesn't mean they're like on life support or anything. It just means that they're at the end of a chain. So let's say, for example, we wanted to make this alkyne. We call it terminal because the last carbon of the chain is involved in a triple bond. You can always recognize a terminal alkyne because there's a hydrogen at the end. So one of the reasons why we have to be careful is when we do this reaction with base, and just a side note, we typically do this in liquid ammonia, which since ammonia is a gas at room temperature, this is done at very, very low temperatures, like usually negative 30 degrees and below. But the ammonia, there's just the solvent. One of the reasons we have to be careful making a terminal alkyne is that that hydrogen on the terminal carbon is slightly acidic. And so if there's base around, which there is, the NH2 is around, it's going to deprotonate it. It is actually strong enough to deprotonate a terminal alkyne. So if we're making a terminal alkyne, we usually have to add what we call a proton source at the very end, like for example, water, and that will reprotonate to make what our intended product is. So to summarize this, if we start with the bromines on the first couple of carbons, and we want to convert this to an alkyne, we'll add water after the reaction has completed as a proton source. Okay, so you can't forget that. So don't be upset if you are making a terminal alkyne on an exam and you forget to put water as a second step, and you might see, a small point deduction because of that, because you won't get your product since it's been deprotonated if it's terminal. All right, so in our next lecture, what we're going to look at is what can we do with terminal alkynes? They're actually pretty unique, and we're going to see something really cool that we can do with them in terms of synthesis.